matrix vector multiplication, right? Where you have a matrix, you have a vector, you multiply the vector with the matrix. And the question is what happens when you do that, right? So when you multiply a matrix with a vector, what happens is the direction of the vector change. If you think of vectors as these pointed arrow kind of things that we used to visualize them as back in uh, back in uh, back in the early days, right? Um, high school level kind of physics, right? So does the direction change? Is the magnitude scaled? Something is both happening, or what, right? Or is it some kind of nonlinear operation that you don't know what happens, right? So here's the question, and we have a specific matrix that is being given here. Obviously, uh, the action does not really depend on what the vector will be, because irrespective of the vector, the matrix is going to apply the same kind of operation, right? Except some specific kind of vectors, like the origin vector, for example, right? 0, 0, where no matter what kind of matrix you hit 0, 0 with, it will always be 0, 0, right? It will not change. So, but in general, what the vector is doesn't matter. What matters is what is the matrix, right? For identifying what kind of operation it is performing. So, yeah, so we have the question, the options. Why don't, so I'll give some time for everyone to look it up, and you can share your answer in the chat. And, in a couple of minutes, I will discuss the solution. Mm, okay, so uh, one has answered, but that's okay. Uh, I will discuss the solution anyway, right? So basically, what happens when we apply a matrix? When we apply a matrix with a vector, right? Uh, we even can think of it as matrix kind of hitting the vector, right? Because order of things is important. So what happens when a matrix basically hits a vector is that you do the matrix vector product, and there's a it's a there's a specialty to this operation, which is that a matrix vector product is a linear operation, right? So it is basically what it is doing is, in general, it is doing two things. It is one, it is either it is scaling the vector, right? So if vector was of certain length, then after the matrix vector product, it can become longer or shorter, right? Other thing that a matrix vector product does is that it rotates the vector in some angle, right? By some angle, right? This is how you can basically visualize matrix vector products. Basically, we have a vector initially, then you stretch it or squeeze it by some value, and also at the same time it kind of rotate it around, right? But so that is the general case, uh, but in this particular example, uh, only one of these things are happening, right? So here what is actually happening is that this vector is rotating. So and you can easily verify this by doing this multiplication, right? So if you do this multiplication, if you multiply 0 minus 1 1 0 with this vector 2 comma 1, basically what you will get is minus 1 comma 2, right? So if you multiply, we get minus 1 comma 2, and and we can obviously see that the magnitude doesn't change, right? So what is the magnitude of vector? Is magnitude of vector is nothing but square root of the square of the sum of squares of all the individual elements in the vector, right? So its magnitude of this vector is square root of 2 square plus 1 square is square root of 5, which is the same as magnitude of the resultant vector, right? Which is also square root of 5. So the magnitude has not changed, right? What has changed is the direction, and we can clearly see, in fact, that the direction, the amount of change in the direction is actually uh, nothing but 90 degrees, right? So it has been rotated by 90 degrees. And in fact, this matrix that I have presented here is kind of a special kind of matrix. It's called a rotation matrix, right? And in general, if you try to rotate, so this is we're talking in like 2D space, where these things are kind of straightforward and simple, right? But in general, if you are basically trying to rotate vectors by angle theta, right? In 2D space, it's angle theta in the counterclockwise direction, right, from x, right? uh, Basically, if you try to do that, then your rotation matrix looks something like this, right? And the way you compute the rotation matrix is also is actually kind of simple. Basically, you consider the two unit vectors in the x direction and in the y direction, and you apply this rotation to them, right? So if you have the unit vector in the x direction, you can represent it as 1 comma 0, right? Because x comes before y. So you take this 1 comma 0 and you apply this theta degree counterclockwise rotation on top of it. So 1 comma 0 becomes gets transformed into cos theta comma sin theta, right? This right? Everyone knows this. So 1 comma 0 goes to cos theta comma sin theta. Similarly, if you have if you consider the unit vector along the y-axis, that is 0 comma 1, and if you apply a theta rotation to it, uh, the resultant vector will be minus sin theta comma cos theta, right? So the y component will be cos theta, and the x component will be sin theta in the negative direction, right? So 1 0 will give you cos theta sin theta, and then 0 1 will give you minus sin theta cos theta, And basically the rotation matrix is nothing but you put in these uh, two kind of uh, rotated vectors together, right? So you take this is the first with respect to the like the rotated vector for the unit vector along the x direction, you put it here, right? So you get cos theta sine theta here, and then for the y direction you put it next to it, get minus sine theta cos theta, and this is your uh, overall kind of rotation matrix. Any vector that is belongs to this two-dimensional space, if you hit the vector with this matrix, it will be rotated by an angle theta in the counterclockwise direction, right? So this is a rotation matrix. Like I said, specifically, if you set theta to be 90 degrees, you get this matrix that we have, right? Cos theta is cos 90 degrees is 0, sine 90 degrees is 1, right? So it's 0, 1, minus 1, 0. That's how you know that this is rotating vectors by 90 degrees in the counterclockwise direction, right? So this is a very broad overview of matrix vector multiplications, what function they perform, right? But this forms the basis of everything in linear algebra, basically, right? Everything in linear algebra kind of flows from the fact that matrix vector products are linear operations, okay? So this is the so now we come to something interesting, which is basis vectors, right? So in the previous example, we saw matrix and matrix vector products. Now here, so basis vectors are basically a way to characterize a certain space, right? So if you have a space of vectors, right? And this concept of a space of vectors, which is also called as a vector space, is a very specific concept, right? So it has a very specific definition, and it has certain properties, right, that are very useful, right? So I will not go into all of those properties because it will be too much of a deep dive into uh, linear algebra. But broadly speaking, if you have something like this, R3, for example, right? R3 is nothing but the three-dimensional space, right? Three-dimensional space of real numbers, right? So each of these coordinates is represented by a real, right? So of course, instead of real numbers, you could also have complex numbers, but we don't go into that complication right now, right? So uh, enough to know that R3 is a vector space, right? So it has these properties like completeness and all. And so specifically R3 over real numbers, right? So it's uh, the over what basically also defines kind of how you want your vectors to be combined. If you want to combine some vectors together, how do you want them to be combined? When you say it's R3 over R, basically you want combining them with scalar factors that are real numbers, right? So you're not multiplying them by complex numbers or anything. So yeah, so briefly, to put it briefly, R3 is what is called as a vector space. You can look up more details about that separately. And vector spaces have this thing called as a basis, right? And one of the properties of the basis is that so the basis is a set that is a subset of this vector space, and the properties of the basis basically is that number one, it is a linearly independent set, which means that none of the elements of the basis, right? So here we have three elements in this basis. So none of the elements in the basis should be representable as a linear combination of the other elements, right? And so that is one. And the second is that it needs to be a generating set, right? Which means that every vector in this vector space or in this R3 space should be mm, should be representable as a linear combination of the vectors inside the basis set, right? So given all these properties, right, and given this set of vectors, the question is very simply, do this do these vectors form a basis of R3, right? So it's very easy. You just check for linear independence of this set, and if they are uh, if they are not linearly independent, then obviously they cannot be a basis, right? So yeah, so I will give some time for people to kind of work it out, and then I will explain the solution. See, okay, so there is one person who answered. Unfortunately, that is not the correct answer. Right. In this case, these vectors do not form a basis R3 because they are actually linearly dependent, right? So, like I said, a linearly independent, if anyway, if vectors are, if a set of vectors are linearly independent, then if you write this equation, right, we add up, we multiply the vectors with some scalar uh, constant, right? So you write Ci Vi, you add it up from I equals to 1 to n, and you equate this sum to the zero vector, right? So if you write this equation, then if all the Vi's are linearly independent, then this equation has only one solution, which is that Ci equals to 0 for all I, right? Which is the trivial solution, obviously. Uh, but in this case, that is not in fact true. In fact, you can write an equation like this, where we take 2 times 1 to 3 plus 3 times 1 1 1 minus 1 times 579, and you will get the 0, right? You will get 0, right? Because 2 times 1 is 2, 3. So if you go like element by element or dimension by dimension, so 2 times 1 is 2 plus 3 minus 5 0. 2 times 2 is 4 plus 3 times 1 minus 7 is 0, and then 2 times 3 is 6, uh, plus 3 times 1 is 9, minus 9 is 0, right? The other way to say this, state this, is that 579 is, this uh, vector 579 is representable as a linear combination of these other two vectors, right? So that is also one way you can say this, which is, this and this are kind of equivalent statement, right? So you can just say that 579 is equal to 2 times 1 to 3 plus 3 times 1, right? That is also true. Uh, it can be anything. I just set the problem up in this way, right? The I have the problem has just been set up like this, right? So yeah, so this is just showing that these three vectors are in fact not linearly independent, and because they are not linearly independent, they obviously cannot form a basis, right? So continuing in this vein, we'll have, let's see, another set of vectors, right? Where, so this is slightly different. So first vector is 1, 0, 0, is also in R3, right? So the first vector is 1, 0, 0. The second is 1, 1, 0. The third is 1, 1, 1, right? And the question is the same actually as the previous question. Does this set of vectors form a basis in R3? Uh, okay, so yes, someone has answered again. Yes, yeah. So this time it is correct. This set of vectors is in fact a basis set for R3, right? And here also, like in the previous case, the same. We will apply the same kind of logic, or same kind of uh, qualifier, right? Qualification test, right? So obviously the set has to be linearly independent, right? And here, you look at how this set is constructed, you will very easily figure out that this is in fact linearly independent, right? So if you consider element by element, for example, so consider this last element, right? So if you number them from the top as one, as index order, right? So it's like first index, second and third index. If you look at the third index, if the third index has to be 0, then uh, you know then this this the product of this must be zero, right? So because this the other two have a zero here, and if you have some non-zero value that is multiplying this 1 1 1, there is no way I can cancel out this last term that appears, right? Similarly, if there is a if you have to make this middle term zero, right, then this one must be zero because you know the same kind of inductive reasoning, we'll find out that uh, these none of these can be expressed as a linear combination of the other, right? So this 1 1 1 can obviously never be expressed as a linear computation of the first and the second because neither of these have a one over here, which this one has, right? Similarly, the others cannot be expressed as a linear combination of the remaining two, right? So 1 0 0 cannot be expressed as a linear combination. These two, because if you have to get rid of something to match this zero, then something else comes in, right? So overall, this does not uh, actually formally, I mean, this is linearly independent, right? So you cannot express any of these vectors as a linear combination of the other vectors, right? And the second thing is that a basis set should be what is called as a generating set, right? So it should be a generating set and it should be linearly independent, which means that uh, every possible vector that belongs to R3 must be expressed in as must be able to be expressed as a linear combination of these three vectors, right? Which is in fact the case, right? We can easily check it out. So for example, if you consider any random vector in R3 that you write as A, B, C, where A, B, and C are all real numbers, right? Then for this set to be a basis set, this any vector that can be written as ABC must be representable as a linear combination of the basis vectors. And it is in fact true, right? So you can write C times 1 1 1 plus B minus C times 1 1 0 plus A minus B times 1 0 0. And what you will be left with is A comma B comma C, right? So because C will come, C is lone, the lone C will come in the final uh, index, right? The second index will is the other two indices will also have C, but those two C values can be cancelled out by this B minus C. So B minus C will cancel out the C values in these two indices. The B will survive in the middle, and A minus B will cancel out the B in the top index, so that only A survives the top index, right? So first index will have A, second will have B, and the third will have C, right? In this way, basically, if you have this set of vectors, then you can span R3, right? You can basically express any possible vector that resides in R3 as a linear combination of these three vectors, and of course they are also linearly independent as well, right? So with that, this is a basis set. Now, so this is kind of a extension of the previous question. Now we have extended the basis set by one more vector, right? So we have added another vector over here. And once again, the question is this still a basis set? Okay, so yeah, so this one seems to be fairly straightforward, right? Just should be, because we have discussed this question multi through multiple uh, we have discussed this concept through multiple questions, right? So obviously this is not a basis set of R3, right? And why it is not, you can reason it in a few different ways, right? One is that you can simply extend the 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 results, right, from the previous question, right? In the previous question, we proved that the first three vectors that form the set over here do in fact form a basis set, right? And if they do form a basis set, then any vector that belongs to R3 can be expressed as a linear combination of them. And in fact, we also showed how that linear combination would look, right? So, for any ABC, we can write something like this. And this is nothing but a vector in R3, right? Which means that obviously this vector is can be expressed as a linear combination of these three vectors, right? Which means that this group of four vectors, or this set of four vectors, is obviously not linearly independent, right? Because you can express this as a linear combination of these three. Very straightforward. The other thing is that the other way to look at it is through dimensions, right? So if we consider this vector space R3, for example, right? So this is the three-dimensional so-called vector space. And when we talk about vector spaces, and this is, this is true for things like R3, or Rn, R2, R3, whatever, etc., Rn, etc., right? Uh, this is true for this kind of vector space, but it's also true for generic vector spaces that may not, you know, neatly fit into this idea of R3, R2, or whatever, right? But generally, the idea is that, or rather, the theory, or the law, or the result is that the size of the basis set decides the dimension of the vector space, right? So if you have a vector space, for example, and you don't know what its dimension should be, which could be the case, right, for some kind of complicated vector space that is not so something very simple like R3, right? So if you have a kind of a complicated uh, complex vector space, or something that you don't really know uh, that much about, all you need to know is how many vectors form the basis of that vector space, right? So the cardinality of the basis set is nothing but the dimension of the vector space. Obviously, R3 is three-dimensional, which means that the cardinality of the vectors of any basis set in R3 uh, should be 3, right? So it can have only three vectors. Uh, more, even more importantly, or rather more generically, like a more general result is that any set, any linearly independent set in R3 can have at most three uh, elements in it, right? So it cannot have more than three. So if you have, at any point of time, you take four elements in R3, then it is no longer linearly dependent. You don't even have to check whether they are linearly dependent or not. You can just say that they are linearly dependent, and it will be true, because that is the result, because that's where dimensions and all comes in. And I don't want to go into much of the details about how you get those results, but it's good to know the results, right? So yeah, like I said, the cardinality of the basis set decides the dimension of the vector space. Obviously, R3 is a three-dimensional vector space, and as such, it can have at most three vectors in any basis set. In fact, it can have at most three vectors in any linearly independent set, right? So because now there are four vectors over here, this is obviously not linearly independent, obviously not a basis, right? So moving on from basis sets and matrix vector product kind of basics, we are coming into something a little bit more directly related to deep learning, which is this idea of eigenvectors and eigenvalues, right? And here, this is a very simple question, which is that given that eigenvalues for a matrix are, these are the eigenvalues, right? 11, 23, minus 32, 4, and minus 5. The question is, which one of these is the dominant eigenvalue, right? Is it is it 11, is it minus 32, 23, or 4, what is it, right? So yeah, so once again, I will give some time for people to think through this and answer in the chat, and we'll see the solution, and then we'll move on to more interesting problems. Okay, so there's a couple of variants, it looks like, in the answers. Uh, so here's the thing: for when you're talking about dominant eigenvalues of a matrix, what you care about actually are the absolute values, right? So you don't care about the signed values. You only care about the absolute values, which means that when you ask like which of these is the dominant eigenvalue, the answer is actually minus 32, right? So minus 32 is actually the dominant eigenvalue because it has the highest absolute value, right? So yeah, it's a very straightforward kind of rule, that dominant eigenvalue is the one with the greatest magnitude, i.e. the greatest absolute value. And we will see exactly why this is the case, right? So we will see. So in the next problem, we will actually see why we care about the greatest absolute value of the greatest, like the eigenvalue with the greatest absolute value rather than the greatest signed value, right? Or rather, we'll see it in a couple of maybe the next question, right? So here, uh, so that was a very simple question, kind of bringing up eigenvalues and eigenvectors, but so this is about the properties of eigenvectors, right? Which of these properties is true, right? We said that eigenvectors of symmetric matrices are orthogonal. So what are orthogonal vectors? So orthogonal just means is is nothing but like uh, the idea that if you multiply two of the vectors, right? So you have a set of eigenvectors, right? And they are kind of indexed by their eigenvalue, right? So if you multiply two eigenvectors that are that that belong to different eigenvalues, right? So one has an eigenvalue of lambda, let's say, and the other has an eigenvalue of mu. And if you multiply the eigenvectors corresponding to these two eigenvalues, then you will get zero, right? So unequal eigenvalues, the eigenvectors corresponding to unequal or distinct eigenvalues, when they do a dot product, when you do an inner product, we will get zero. So that is the definition of orthogonal here, right? So here I'm talking about set of eigenvectors, but obviously an orthogonal set can be a set of any vectors, right? So we're specifically talking about a set of eigenvectors of the matrix, right? And a symmetric matrix is one in which if you take the transpose of the matrix, you get the same matrix, right? So basically, you have the diagonal and the upper triangle part of the matrix, right? The part of the matrix that resides above the diagonal is exactly mirror image of the part of the matrix that resides in the lower triangle, right? Below the diagonal. So if you take a transpose, which is nothing but like rotating around the diagonal, the matrix, if you take a transpose, you'll get the exact same matrix back, right? So A transpose is equal to A, right? So that's what a symmetric matrix is. And I have explained what is the meaning of an orthogonal set of vectors. The second part is that eigenvectors with distinct values form a basis. We have already discussed what is a basis, right? So I will not go over it again. Eigenvectors of any matrix A belonging to R n by n, which means that this is a square matrix of n rows and n columns having distinct values, right? So these eigenvectors, all of the eigenvalues are distinct, are linearly independent, and D is all of the above, right? So this question kind of deals with all of the properties of eigenvectors, right? And so we will see kind of short proof sketches of some of these properties, right? Yeah, so I'll give, once again, I'll give some time for people to kind of absorb the question and then see the answer and the solution. And kind of briefly talk about the proofs of these things. Okay, so let's see. So yeah, so like people have answered, some people have answered. The answer is indeed D, right? Of course, all of the above. Um, just kind of the purpose of this question, right? To kind of describe and explain the properties of eigenvectors, and see kind of short proofs as to why this or how these properties can come to be, right? So yeah, so obviously, so we will start off with the easier one, and then we will see. So A is kind of the easier. um, so we'll start off with A, and then we will see like C, and uh, if C is true, right? So then B kind of follows from C, right? Obviously, if you have like distinct values of the eigenvalue, distinct eigenvalues, then you will have n distinct eigenvectors, and if you have n distinct eigenvectors that are linearly independent, then obviously they will form a basis, right? They will form a basis of this Rn n-dimensional vector space. Okay? So we will see the proof for A, and we will see the proof for C. And like I have explained, if C is true, then B follows from it, right? So that B is basically corollary. B is basically a corollary of C, right? So start with option A. So we just consider symmetric matrix A, that is, so A transpose is equal to A because it is a symmetric matrix, and we consider two eigenvectors x and y with distinct values, right? So the eigenvalue corresponding to x is lambda, and the eigenvalue corresponding to y is mu. Then we can write, so here we just kind of use a little bit of matrix trickery, little bit, right? So we write A x transpose y is equal to x transpose A transpose y, right? So here what we are doing is we are taking this transpose operation inside the bracket, right? So when you have AX and when you have like a product of two matrices, or you have a product of a matrix, of a vector and a matrix and a vector, and you take the transpose, what happens, right? So you have, let's say, A B whole transpose, where A and B are so let's say matrices. So if you take AB transpose, it is nothing but B transpose A transpose. Basically what happens is when you pull the transpose operation inside the bracket, you have to reverse the order of the operations, right? So AB whole transpose is nothing but B transpose A transpose, which is what we see over here, right? So AX whole transpose is nothing but X transpose A transpose, right? So X transpose A transpose, and then we utilize the associative property of matrix vector products, or even matrix multiplications, right? So we draw the uh, we can basically put the brackets anywhere that we like, right? So we put the brackets around A transpose Y, right? So now we have X transpose A transpose Y, and of course, uh, you know, A transpose is equal to A. So we can just replace this A transpose with A because A is a symmetric matrix. So now it becomes X transpose times A transpose Y. But AX is nothing but lambda X, because X is an eigenvector with lambda being the eigenvalue corresponding to it, whereas a Y is nothing but mu times Y, because Y is also a eigenvector with mu being its eigenvalue, right? So so if we evaluate this part, this uh, equation AX transpose times Y, we'll get lambda times X transpose Y, and if we evaluate the final equation, X transpose AY, we'll get mu times X transpose Y, right? And we are given that lambda and mu are distinct values, which means that to have both of these uh, equate to the same value, X transpose Y must be 0, right? Since lambda and mu are distinct, then X transpose Y must be 0. Essentially, what you are going to get is uh, mu times X transpose Y equals to lambda times X transpose Y, and then you put them on one side, you'll get lambda minus mu times X transpose Y equals to 0, and we are given that lambda and mu are distinct, which means that lambda minus mu cannot be 0. So X transpose Y must be 0, right? So that is the proof of orthogonality of eigenvectors of symmetric matrices with like distinct eigenvalues. Second part for option C, which is the linear independence of distinct eigenvalues, we note that so here the first part here is nothing but the definition of the proof of linear independence, right? So if set of vectors vi is linearly dependent, then there should exist some set of Cj, which are kind of which are real number scalars, where not not all of them are 0, such that this linear combination of vi's must be equal to 0, right? Where vi's are the eigenvectors with distinct eigenvalues lambda, right? So we take this equation and we multiply it. So this is kind of a proof technique that is being applied. So you take this equation and you multiply it with this polynomial, right? So this is a polynomial where you take a minus lambda I times I is the identity matrix, and you have multiplied it n minus 1 times. You're skipping I equals to 1, so you're starting from I equals to 2 and going n, right? And if you multiply this, what you will basically be left with is a polynomial in lambda 1 times c1 times v1, right? Because uh, yeah, so where p lambda is a polynomial function, lambda minus lambda I, product of lambda minus lambda I going from 2 to n, right? And since all of these lambda i's are distinct, p of lambda 1 is obviously not equal to 0, right? Because, you know, at no point does lambda 1 is not represented in this product, which means that you're taking a difference with all distinct numbers, with all numbers that are different from lambda 1, which means that all of the numbers that you're multiplying are non-zero. So output will also be obviously non-zero, right? So p of lambda 1 is not equal to 0, which means that c1 must be 0, right? P of lambda 1 is not equal to 0, then c1 must be 0, because only then we'll get the 0 vector over here, right? So that shows you for c1, and then you can repeatedly apply the same method again and again, right? So you take next time what you do is you take this product, but you change it. Instead of skipping I equals to 1, you skip I equals to 2, right? So you multiply a minus lambda 1i, and then you go a minus lambda 3i, lambda 4i, and so on. And then you will be able to show that c2 must also be equal to 0, and then c3 must also be equal to 0, and so on and so forth, until you show that all of these ci's must be equal to 0. If we are to, if you are to get the sum of ci vi equal to 0, right? In that way, basically, you can show that eigenvectors and distinct eigenvectors will always form a linearly independent set. And of course, here eigenvectors are kind of defined for n cross n matrices, which means that uh, there are going to be n different eigenvectors, and you know they will obviously form a basis, right? Because they are n eigenvectors of dimension n that are linearly independent, right? And the maximal linearly independent set uh, in any Rn, so obviously we'll have n elements, and it will form a basis, right? So option B follows from option C. Obviously, option C we have kind of shown through kind of technique, right? It's a proof technique. And option A we have already seen, right? So that's why all of the above. right? So now we will see kind of a little bit more practical implication implications of eigenvectors, um, or specifically like eigenvalue decomposition as it is called. So we consider matrix A, and we say that the dominant eigenvalue of a matrix A is lambda t, t for dominant, right? What happens? The question is what happens to this sequence? So we have some vector x0. We don't know what this vector is, right? Then we do like we multiply x0 times identity. So this is just the original x0, and we have a x0, then a square x0, and so on and so forth. So the question is what happens to this sequence if lambda t the absolute value of lambda t, or um, yeah, absolute value of lambda t is less than 1, right? So lambda d is the dominant eigenvalue, right? Obviously, and in the previous question we have already seen that dominant eigenvalues, like the definition of dominant eigenvalues does not care about the sign, right? So we care about the absolute value rather than the signed value, right? That's why here the specification is that the absolute value of lambda d is less than 1, right? So uh, yeah, and then you can assume that this n cross n matrix A has n distinct valued n distinct eigenvalues, right? Which kind of brings in all of those other nice properties, right? Which means that eigenvectors from a basis, uh, the they form like a linearly independent set and all that stuff, right? Okay, so uh, yeah, so we have a situation where, so here we have a situation where we're kind of repeatedly multiplying this matrix A, right? Which is obviously only possible if the matrix A is n by n, right? Because you have to take care of the uh, matrix multiplication rules. So yeah, we are multiplying repeatedly by this matrix A, and in fact, what will happen if the eigenvalue, if the dominant eigenvalue is less than 1, is that this sequence will vanish eventually, right? And why that will happen is a nice, interesting thing. And the proof of why this will happen kind of relies on these assumptions, right? That this is a matrix that has n distinct eigenvalues, right? Because then what happens is that once you have n distinct eigenvalues, then you're assured that you will have like n distinct eigenvectors uh, that are all linearly independent, right? And the n distinct eigenvectors that are linearly independent will form a basis in Rn, right? And if you have a basis in Rn, then any vector in Rn, such as x0 that we have over here, this x0 can be represented as a linear combination uh, of the of the basis vectors, right? Essentially, and in this case, the basis vectors are nothing but the eigenvectors, right? So yeah, so all of that background basically is what I said over here. So the eigenvectors of A, that is v1, v2, vn, they are linearly independent because the eigenvalues are distinct, which means they form a basis, right? Because you have n of these values and A is n by n, so they form a basis of of Rn specifically, right? So basis of Rn, right? Which means that x0, which is a vector in Rn, which is an n-dimensional vector, can obviously be expressed as a linear combination of these vectors, right? Which means that we can write x0 equals a1 v1 plus a2 v2 plus an vn, where a1, a2, and an, etc. are real numbers, like scalar multiples. And then we basically write this term, right? So this is the kth term of the sequence, a raised to the power k x0, and this is nothing but we're basically multiplying a again and again, right? So it's a times a times a times a dot 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 k times, then multiplied by x0, right? So this is how this thing essentially is going to happen. And what we have here, basically we can divide it, we can split it into two halves. One half is k a to the power k minus 1, and then the remaining part is a times x0, right? So it is a to the power k minus 1 times a times x0, and x0 can be written as a linear combination of the eigenvectors of A, right? And then when you use the distributive property of matrix multiplication, you can basically apply this A times you multiply with A for all of these different vectors separately, right? So you distribute this multiplication with A over this sum, right? And what you get is nothing but lambda times a1 times v plus lambda 2 times a2 times v2 plus lambda n times an times v, right? Because a1 a2 sorry v1 v2 vn are eigenvectors of A, and when you multiply a matrix with its eigenvector, you get the eigenvalue multiplied by that eigenvector, right? This is the eigenvalue equation. Uh, a v1 equals lambda 1 times v1 for vi rather, for as lambda I times vi, as vi is an eigenvector of A, right? So this is a to the power k minus 1 multiplied by some of these vectors. Now you take another a out of this a to the power k minus 1 and you multiply it with this uh, vector, and you get lambda 1 square times a1 v1 plus lambda 2 square times a2 v2 and so on, multiplied by, of course, a to the power k minus 2, and you can keep doing it over and over again until you have multiplied all of these k times a matrices, and essentially what you will be left with is lambda 1 to the power of k a1 v1, lambda 2 to the power of k a2 v2, and so on until lambda n to the power k an vn, right? And if k is large enough, what will happen is that the dominant eigenvalue term, right, which is lambda d term, will will basically dominate over all the other terms, right? So it will overpower everything else, and only that particular term will kind of determine what the value will be. And if the absolute value is less than 1, then what will happen is that uh, this value will vanish, right? It will vanish to 0 because you multiply lambda d raised to the power k, and if lambda d is less than 1, then it will approach 0, and that is the dominant term, right? uh, the dominant term itself is approaching 0, then every other term is like already dead, right? So they're all also gone. Everything will kind of approach towards 0, right? So related question is what will happen if the absolute value of the lambda d is equal to 1, right? Because I think based on the previous discussion, it is quite clear what will happen if lambda d if the absolute value of lambda d is greater than 1, right? Obviously it will kind of blow up the vector, because you do lambda d to the power of k, and if lambda d is greater than 1, then that will tend towards infinity, right? So you'll get larger and larger vectors, right? So what will happen uh, if this is the case, right? If it is exactly 1, what will happen then, right? And this, I mean, even this part is kind of follows from the previous discussion. You can easily figure it out, right? Based on the final form of that equation that we got. Yes. Yeah, I mean, if x naught lies in the span of the distinct eigenvalues, then distinct eigenvectors, then obviously you can express it as a combination of those distinct eigenvectors, and then all of the discussion preceding is valid, right? Obviously, for a general a0, a you know a0, if a0 can be anything, then we require that this matrix has this, yeah, distinct values. Yes. Uh, yeah. So this kind of I mean, if this is true, then what happens is that it will kind of reach a steady state situation, right? So if lambda d, if we look into this equation, essentially what will happen is that the lambda d term, which is the dominant term, that will kind of survive, and everything else will die to 0 asymptotically, right? Because if the dominant eigenvalue is equal to 1, then that means that every other eigenvalue is less than 1, right? So when you multiply them by themselves over and over again, they are going to die to 0, and then you will have a situation where if where the sign kind of becomes important, right? Where if lambda t is equal to +1, then you will basically have like the same value throughout, right? So, then lambda d times k will always be 1, and essentially what we'll be left with is AD times VD, right? So you'll end up at one particular vector, uh, which is some multiple of the eigenvector of the dominant eigenvalue, right? So you'll end up there. If the other case, if lambda d is equal to -1 instead, then what will happen is that you'll go from, plus that value to minus that value and so on and so forth, right? So you'll kind of toggle between two different values, but overall, even then, you have kind of reached a steady state situation, right? So yeah, so that's dealing with the end of kind of that discussion. So we come now to uh, simpler problems. Uh, so here there are two features, P and Q, right? So you have one feature P and another feature Q, and basically what you have here are different samples of these features, right? Different samples and what feature values of P and Q you get for those samples, right? So the first sample you get one for both, then you get 3 and 3.2, 5.96, 4.6 and 5, and so on and so forth, right? So the question here is that, do we get some additional information by considering both of these features, or do we not get, in which case we can remove one of these features, right? And it's a very simple question, right? All you need to do is visual inspection. And the answer should be very straightforward. Yeah, so like I said, it's a very simple question. All you need kind of is visual inspection, and just by looking at this data, you can kind of figure out that you won't get much additional, you're not really getting much additional information by considering these two features separately, right? Because, the values are very close to each other, right? So when you get P equals to 1, you get Q also equals to 1, 3 and 3.2, 4.9 and 5.9 and 6, right? 8 and 7.8 and 7 and 5 are kind of identical again, right? So you can basically just take one of these features, you can take either P or Q and can teach the other, and the amount of information that your model receives, right? So these are features that will be fed into a model to kind of ultimately do something, right? To ultimately do a classification or a regression or something, right? So the amount of information that your model receives will not really change whether you have one of these two features or you have both of these features, right? Uh, in fact, if you discard one of these features, then the complexity of your model will reduce a bit, because now we have one less feature to worry about, so there are fewer parameters and so on and so on, right? So, okay. So yeah, so one of these features can be removed because they are highly correlated. Uh, if you have a question, why don't you type it out in the chat? Uh, then we will address it. Okay. So then another similar question, right? But here we are kind of giving, yeah. Yes, yes. Uh, no, I mean in this, but in this question in particular, it is just this is just visual inspection. uh, the metric that you can use are the are, like correlation coefficients, right? So you can find out if two, if, let's say you have samples, right? You have 100 samples of data, you have 10 features, right? And you can compute the correlation matrix of this of those features, and essentially what you will be left with is a 10 by 10 matrix, where where each like ij term, ij element will be the correlation between the ith feature and the jth feature. And obviously, because ij and ji are kind of interchangeable here, right? Correlation does not care the order of the features that you feed into it. It will be kind of a symmetric matrix, and all that kind of properties will apply, right? So essentially, you compute what is called as the uh, correlation correlation matrix, and then you can discard features that are highly correlated, right? So you can set a correlation threshold that if they are more than 0.95, if the correlation is more than 0.95, then I discard that feature. I mean, discard one of those features, and so on and so forth. And by that, doing that, you can basically reduce the number of features uh, that you deal with, right? So that, yeah. Uh, yeah, so it will kind of depend on, so that the whatever threshold you want to set, kind of, so that it is a hyperparameter, right? Like we have we have treated, basically models will have parameters and hyperparameters, right? And what happens is that, let's say you set a lower value. So you set a lower value of threshold. You say that all features uh, that are zero point 0.8, that have correlation of zero point 0.8 or higher, they I don't care about having both of those features, right? So if you set at zero point 0.8, then you will reduce the number of features that you're going to do more drastically, right? That you consider more drastically than if you had set the threshold as 0.95. If you had set the threshold even higher at say 0.99, then you would have basically almost all of the features that you started off with, right? And you'll have a bigger model, and hopefully maybe you get like a slightly better performance. So kind of a trade-off, right? If you set the threshold at lower values, then you will be dealing with fewer features, which means your model will be simpler, right? uh, if you consider more and more features, then your model will be more complex, and maybe you can get better classification or better regression or whatever out of it, right? So it all comes down to these trade-offs. And then you also have to consider like overfitting and all that things, right? So it becomes very complicated, right? The only kind of rule of law that you can consider is that you set these threshold values. Let's say you are using principal component analysis to kind of reduce the number of input features that go into your model, right? Then you set these thresholds, and you kind of find out uh, at what value of the threshold do I get like optimal performance, right? So that's the way to do it. Okay. So yeah, so then we consider similar question, but with like named features, right? So let's say you have these different features, name, age, and that stuff, and you want to identify attributes that are highly correlated. And obviously, this is a very straightforward question, right? Obviously, answer is C. Someone has already pointed out, right? This is nothing but the same value, right? It's height in inches is nothing but a scaling factor difference in from the height in centimeter, right? So it's just some factor multiplied by the height in centimeter, which means that they are kind of perfectly correlated. In fact, uh, if you compute the correlation coefficient between height in inches and height in centimeter, you'd get exactly one, right? Because because they're kind of exactly the same. It's just a matter of scaling factor, right? So if we have height in any one of the uh, measures, then we don't need any other measure, right? So yeah, then so this is a kind of a short question. I think it was kind of feedback from an earlier session, but the question basically very simple is, are the PCA eigenvectors orthogonal? So PCA is this technique that you apply, principal component analysis, where which we kind of briefly discussed, right? So in PCA, you basically apply uh, eigenvector, eigenvalue decomposition on X transpose X, where X kind of is your entire data, right? So X is basically your n samples by n features, right? Number of samples by number of features, and then you do X transpose X, right? And essentially you get a vector, right, sorry, you get a matrix that is num features by num features, which is a correlation matrix, right? What is important, of course, is that before you do this X transpose X business, you have to do a standardize, you have to scale the features in such a way that they become zero mean and unit variance, right? So that is very important. Scaling is kind of important to apply all of these techniques afterwards. So you scale them, and then you do X transpose X, and then you do eigenvalue decomposition on it, right? And the question is, are these eigenvectors orthogonal? And yes, so they are in fact orthogonal. And the reason they are orthogonal is because X transpose X is a symmetric matrix, right? So if you take the transpose of X transpose X, you can basically, so uh, you pull the transpose operation inside the brackets, right? And then when you pull the transpose inside, you have to switch the order of operations. So X transpose X whole transpose is nothing but X transpose times X transpose transpose, right? And X transpose transpose is nothing but X. So you apply transpose two times, it just rotates back to its original configuration. You get the same matrix out. So ultimately, you are getting basically that the transpose of X transpose X is nothing but X transpose X. So it is symmetric matrix, which means that eigenvectors will be orthogonal, right? So this is something we have already seen earlier. So that is the end of the material. I want to briefly show a kind of hands-on example with this thing. 2 minutes separately. Okay, so I have switched over here. So we have, okay, so I have switched the Chrome. Let me share screen. Share screen. Good. All right. So yeah, so I just want to give a kind of brief overview. So since we are talking about PCA, I want to give a brief overview of one of the use cases of PCA, right? Or even you might think one of the use cases of uh, eigenvalue decompositions, just to say that you might want to visualize something, right? So you have some high dimensional data, and you want to kind of view what the data looks like, right? And PCA is something that can help to do that, right? Uh, yeah. So we have set this. Let's do this. Yes, this is nothing but, so this is just loading the data set. So we are loading MNIST data set, which hope you remember. I mean, if you have been in my sessions earlier, right, we have uh, we have uh, trained a one hidden layer neural network on MNIST, right? Kind of an introductory thing. Um, so, but I will kind of introduce it again. So MNIST kind of looks like this, right? Handwritten digits that are 28 by 28 size, right? You can see it kind of different. Yeah, so this is an 8, for example, right? So images that look like this. So this is a 28 by 28 image, right? At the at the maximum level, what this means is that there are 784 different features, right? Maximum possible, right? Because if you consider each pixel of this image as a feature, then 28 by 28 is 784 pixels, right? So that is the number of features that you can get, right? So we are going to do visualization. We're going to use PCA for visualization, essentially, right? So here, basically, we are kind of taking a smaller subset of the data, right? The MNIST train set had 42,000 examples. We're taking 15,000 out of them, right? So that's why shape of the sample data is 15,000 by 784. And then we do data pre-processing, which is what I was talking about earlier, right? So we apply this thing called standard scalar, and what standard scalar does is that it makes the data have zero mean and unit variance, right? So mean equals to 0, variance equal to sigma equals to 1, and you apply that. Shape obviously doesn't change, right? It's just the values that inside that have changed, right? And then we compute the variance matrix, or rather the covariance matrix, right? So you take sample data transpose and you multiply it with sample data, right? So this is A transpose A, right? And our A is 15,000 by 784. A transpose is 784 by 15,000. So we do the matrix multiplication, we get 784 by 784. This is our matrix of covariances, right? Where each ij element is the covariance of the ith pixel with respect to the jth pixel, right? And the diagonal terms are basically the variance of each pixel kind of independently, separately, right? So now we come to the actual eigenvector decomposition. So we are using SciPy SciPy library here, scipy.linalg. Linalg, scipy.linalg is basically linear algebra library of linear algebra implementation of scipy, kind of useful, right? So we get eigenvalue decomposition function, and uh, yeah, so we apply the eigenvalue decomposition on the covariance matrix, right? And we pick the two highest eigenvalues, right? In fact, so why we set the 782 and 783 is because this function h returns the eigenvalues in ascending order, which means that it returns the uh, lowest eigenvalue first at at uh, index 0, and the highest eigenvalue at index 783, right? And if you want the highest two eigenvalues, you pick 782 and 783, obviously, right? And we need the two highest eigenvalues because we want to kind of visualize the data in a 2D scatter plot, let's say, right? So we get this data, right? And then uh, shape of eigenvectors is nothing but this 2 by 784. Yeah. So this here, right? Values and vectors. This returns everything. So values, let's say here, no, I mean, it will return everything if you don't specify which ones you want to pick. But here, what we are picking is we're picking the two highest values. Picking two. So that is because this function generates it returns the eigenvalues in ascending order, right? So it returns it will return a list of the eigenvalues, and uh, because this is a 784 by 784 matrix, essentially what it will return is a list of 784 values, right? And it will sort that list in ascending order and it will send, which means that at index 0 you'll get the smallest eigenvalue, and at index 783 you'll get the largest eigenvalue, right? So at 783 you get the largest, then at 782 you'll get the second largest. So we're just picking the two largest eigenvalues because that's what we care about, right? Right. Yeah. So the dominant lambda will be 783. Uh, s- so so the vanishing and exploding value is kind of only relevant when you are doing multiple multiplication, like you're doing repeated multiplications with the same matrix, right? So this is something little different. So here we are doing PCA analysis to visualize the data set, right? So here we are kind of concerned about the most relevant eigenvectors that kind of describe the data that we have been given, right? And we'll see what these eigenvectors actually look like, right? So uh, if we plot, so this is the first eigenvector, right? And this is the second eigenvector. So this is what the most like relevant most dominant eigenvector looks like. Is the second most dominant eigenvector, and then there will be like 782 more of these things, right? And the way you understand is that if you consider any like MNIST digit, like any sample that looks like this, what it kind of boils down to finally is that any MNIST sample can be expressed as a linear combination of these eigenvectors, right? So it can be expressed as like a sum a1 times this eigenvector plus a2 times this eigenvector plus a3 times the third, and so on and so forth until you have added up uh, linear combinations of scaled combinations of all the eigenvectors, right? So yeah, so that's what that is. And then yeah, so we break this down, and so we basically project it down, right? So our our original data is 784 dimensions. 784 dimensions. I have taken 1,000 samples out of it, right? So this is our original kind of data, and now I am taking a projection of this data along these two eigenvectors, right? So we have picked two eigenvectors. and we are taking the projections of our data along these two eigenvectors, right? So that's why we do this matrix multiplication over here. Yeah, that's why we do this matmul, right? This will generate the projection of the samples along these two eigenvectors, and then we can plot them, right? Plot them over here. Yeah. So this is what the data kind of broadly looks like in this is what the data looks like in the uh, in 2 dimensions, right? So if you apply this PCA analysis and then you plot the data along the two principles, right? So this is the first principle, which is the projection along the first eigenvector, right? Eigenvector 1 over here, first feminist eigenvector, and then this is the second principle, which is a projection of any sample along the second eigenvector, right? And here you have, so this is kind of a nice visualization, which was obviously not possible in the raw data set, right? Because the raw data set had 784 dimensions, and there is no way that we can kind of visualize that because we are kind of stuck in this 2D max to max 3D paradigm, right? Even 3D, you cannot really visualize on a screen, for example, because the screen is two-dimensional, right? So with PCA, we have like a relevant or a meaningful transformation that brings down that dimensionality from the very high dimension 783 or something down to a 2 dimensions, so that we can plot and we can see some of these characteristics, right? So, how they are kind of clustered together, what classes are next to what other classes, right? Which classes are, more clustered, which classes are more spread out, things like that. So, yeah, I mean, it can be little useful to see this. And of course, when you apply PCA, you can also do dimensionality reduction and kind of reduce the dimensions of the input that goes into your network, right? So that is also one possibility. And this is the same thing, but with a slightly different, with a different implementation. So in the previous example, we were using SciPy, and here we are using scikit-learn, which is this sklearn, excuse me, which is this sklearn library from which you can download this decomposition class, and from that you get this is a PCA decomposition. And you can set the number of components that you want out of this decomposition. Here we have set it to 2 because we want to visualize it, right? Instead, you could set it to some higher number if your main idea or if your main target was to kind of reduce the dimensionality of your input. You could have set it to like 100 or 500 or something like that, right? Because then you would have reduced your dimensions from 783 to, let's say, 100, which is a almost 8x reduction. And then you can set that 100 dimension input to a deep learning neural network like a multi-layer perceptron and do classification, right? So that is one thing you can do. So yeah, so you just set the number of components, and then you do a fit transform on the sample data, and ultimately what you get is PCA data, which is reduced dimensionality reduced data, right? So you get, since you have set number of components to 2, we get uh, 2-dimensional data, and then I pick out like some of these samples out of these 15,000, and then I just plot them on a scatter plot to kind of visualize in the same way that we were visualizing earlier, right? So yeah, I mean, here it kind of looks like a rotated version of the same plot, actually, if you look at it. Right? But yeah, so that's it. This is visualization. So I have shown visualization here. You can separately try to implement uh, dimensionality reduction as well, right? Uh, yeah, that's it. Multiplication, uh, which one? This one? Yeah, so this multiplication is nothing but taking the projection of the sample data along the two eigenvector, along the two eigenvectors, right? So how do you take a projection of one vector? So let's go let's go down to the basics, right? So how do you take a projection of one vector along another vector? Uh, right? If you ask, if I ask you how do you take a projection of one vector along another vector, the answer is pretty simple, right? You take the inner product of those two vectors, right? So you take the inner product of one vector with the other vector, and that will give you the projection of this vector along that direction, right? So that's exactly what we are doing here. There is nothing more. And of course, I mean, I'm simplifying things a lot, right? Obviously, that vector along which direction you are taking the projection, that has to be like a unit vector, so that your values are kind of preserved, right? So I'm not going into that, but essentially, uh, no, no, it is not. A projection is nothing about representation of information, right? Uh, Projection is just projection, right? It's the you draw this, you draw you draw a vector, let's say in two-dimensional space, right? So you draw a vector that is x x comma y, let's say, right? And then let's say you want to take the projection along the x-axis and you want to take the projection along the y-axis. So you take a dot product of that vector with the unit vector along the x-axis. You'll get x, which is the projection of that vector along the x-axis. And then you take a dot product of that vector with a unit vector along the y-axis. You'll get y, which is the projection of that vector along the y-axis, right? So x and y are basically the projections of the vectors along x-axis and the y-axis, right? Here also you are doing something very, very analogous, right? Because especially because this covariance matrix is symmetric, which means that the eigenvectors are orthogonal, right? So you are taking projections along orthogonal dimensions, and specifically you are taking projections, in this case you are taking projections only along two of those orthogonal dimensions, so you're getting like a two-dimensional output out of it, right? So yeah, so uh it is basically you're setting the directions based on the data that you have been provided, right? So one, obviously you can consider that, I consider a unit vector. So if it is, if for this 28 by 28 images, there are 784 points, right? That you can have. So you can consider a unit vector along each of those pixel values, right? So you can set 1 0 0 0, 783 times zeros. So that could be one unit vector, and so on and so forth. And if you take the projection along those dimensions, then what you will end up with is nothing but like the pixel values that you have, right? So that is kind of a meaningless set of uh, set of orthogonal vectors along which you can take projection. uh, what you get out of PCA is kind of a meaningful set of orthogonal vectors along which you can take a projection. And in fact, these orthogonal vectors are also kind of ordered based on how important or how meaningful they are, right? So you are getting a new set of vectors, and then you know that the the vector with the highest eigenvalue is the most important direction along which I have to check my projection. Then the next one will be the next most important, and so on and so forth, right? All based on what kind of data you have fed to the system. So yeah. Mm. No, you multiply the data, right? You get the covariance of the data, and then you perform PCA on the covariance matrix. You are not performing PCA on the eigenvectors or the eigenmatrices. Yeah. Yes. Then you will get the eigenvectors, and you get the eigenvectors in order of their importance, essentially, right? And then based on that, you can do whatever. You can do dimensionality reduction, you can do data visualization, you can do all sorts of things. Okay, so I think which multiplication? Yes, this one, this one. Yeah, no, this is not covariance, right? Covariance was earlier when we generated the covariance matrix. This one, like I said, is we are taking the projection of the samples along the directions of the eigenvectors. That's it. Yeah. You just revise, some vector basics. I think that would be helpful. Otherwise, it will be very difficult to understand. Okay, I think so. That's with that we can conclude today's session, right? Thank you.